Hi, I'm Jerry Machado. I'm the new business development manager for Panasonic's passive components, and today I'll be presenting a little bit about our film capacitors, inductors, and hybrid capacitors for autonomous vehicles. We'll begin with a quick presentation of our film capacitors. They're outstanding for DC-DC and AC-DC converter applications in a variety of autonomous and electrically powered vehicles. As we all know, electrically powered vehicles are becoming more and more dominant out there in the marketplace today for a variety of reasons, including uh, environmental and safety and requirements for larger batteries and capacities. Our film capacitors are ideally positioned to accommodate these issues. They're fully compliant with AEC Q200. They provide a high level of safety with our segmented metallization technology, which I'll be going into a little bit later. We can support a high level of ripple current, and we're optimized to exist in high humidity, high heat environments. And this is all a function of a couple things. Our vapor deposition capability. We have ability to put down patterns with an interesting fuse option, uh, heavy edge deposition capability to accommodate higher currents. And we've developed a unique potting resin that allows us to operate in the high humidity, high temperature environments. And if you look at the slide on the lower right-hand side, you'll see kind of an overview of the capacitors as they exist with the metallization and the dielectric film. And the interesting part is that in the fuse pattern on the lower right-hand side, you can see that if you have a fault in the dielectric where you have a short circuit, the current will burn those fuses out, thus eliminating that segment from the capacitor, lowering the capacitance a tiny bit, but giving you overall same capacitance at the same voltage, giving you a longer lifetime in specific applications. And you find these capacitors on a wide variety of applications in the charger world, both onboard as well as wall chargers. And you can see block diagrams of several different chargers here in this slide. And at the top, there are a number of numbers in there, and that's where you would find our different capacitors. We have input capacitors, which are safety capacitors for AC-DC converters, like number 1 in the wall box charging application. And you can see that you need, the safety capacitors in a variety, all of the applications, as well as the filtering applications, the DC link applications, and the output filtering applications. Moving on to our power chip coils, our PCC inductors. This is an interesting inductor. It's different from a standard ferrite inductor that's wound. These inductors the windings are encased in a metal composite that locks them into place and gives them a number of characteristics that you wouldn't find in a standard inductor. And you can see these on the DC bias characteristics where you have inductance plotted as a function of current. And standard inductors saturate. That's the way inductors work. Ours saturate as well, but at much lower rate. We call this soft saturation. So the inductance remains somewhat the same over current. And if you look at impedance as a function of frequency, our metal composite inductors change much slower in the standard ferrite type. The windings themselves are encased in this metal composite matrix that holds them in place. So the inductors will not hum at any kind of frequency, and that is aesthetically pleasing in a lot of applications. And finally, thermal conductivity characteristics of our metal composite inductors are superior to what you would find in a standard ferrite type. And if you look at our inductors compared to several other inductors like from Vishay and for TDK, you'll see that our metal composite is similar to Vishay's, but we have capabilities of higher voltage, and TDK's, their ferrite inductors are somewhat different, again, from our metal composites. So we have the soft saturation capability. We can accommodate more current through our soft saturation, and our temperature characteristics are somewhat better. And oftentimes it's difficult to to have a second source for inductors, but our metal composite inductors can replace very easily the Vishay LP or LC series of inductors. And you can see the footprints shown here, going from 5.5 up to 10 by 10 for the Vishay inductors, the LP series, and for the TDK inductors from 6.6 to 7.7 by 7. Moving on to hybrid capacitors. Hybrid capacitors, interesting capacitors. It combines the best of both worlds of electrolytic with polymer capacitors. You get, with electrolytic capacitors, you get high reliability from the electrolyte. You get the advantages of high voltage, high temperature, low leakage current, and you combine that with the polymer electrolyte, where you get a large current, low ESR, small size, and higher conductivity. And the hybrid capacitors themselves are all AEC-Q 200 compliant and can be used in a wide variety of electric vehicles and autonomous vehicles out there. The capacitor itself, as I mentioned before, combines the electrolyte of both the polymer and the electrolytic capacitor. And you can see that you get really excellent electrical conductivity. The conductive polymer is about 10,000 times more conductive than the electrolyte, and the electrolyte gives you the high voltage characteristics. So you get low ESR, low current, high reliability, long life, high voltage, and large capacitance. And I should mention temperatures up to 125 degrees C.
Panasonic Industry.